Okay, so here we have a problem. A fish swimming behind an oil tanker gets caught in a whirlpool created by the ship's propellers. The fish has an angular speed of 2 radians per second. If the water in the whirlpool accelerates at a constant rate of 3.5 radians per second squared, what will the fish's instantaneous angular speed be 2.5 seconds later? Okay, we're going to go ahead and do this problem just like we've done all other problems. We're going to start with a picture. So we've got this fish swimming by an oil tanker and it gets caught in a whirlpool created by the ship's propellers. So here's the ship's propellers. Okay, here's my fish swimming in the water. And it is going to get caught in the whirlpool and start rotating around. Okay, then we want to write down our givens. Well, it says the fish has an angular speed of 2 radians per second. So you can think of this. This is a speed, okay? What we need to remember is it's an angular speed. So instead of using the letter V, okay, we need to use the letter omega. Okay, so we've got this angular speed of 2 radians per second. Okay, then it says if the water in the whirlpool accelerates at a constant rate of 3.5 radians per second squared. So we've got an acceleration here, but again, it's an angular acceleration. Okay, so I can write down it is 3.5 radians per second squared, and it is an angular acceleration. So the Greek letter for acceleration is alpha. Okay, so we've got our angular acceleration. It says, what will the fish's instantaneous angular speed be 2.5 seconds later? 2.5 seconds, well, time, thankfully, is always the same. There's no difference for the linear or the angular. So 2.5 seconds, still going to be delta t. Okay, and it wants to know, what will the fish's instantaneous angular speed be? So we're trying to find an angular speed. A speed, again, not the letter V this time, instead the Greek letter omega. And we already have an omega. Well, this is what the speed is starting out at. It says the fish has this speed. It wants to know what will its speed be 2.5 seconds later. So this is what it's starting as. This is our initial speed, and we want to know what it's going to be later, our final speed. Okay, so we've got our pictures, our givens, and our find. We need to choose an equation. So we're going to go and look at our equations that we had. Okay, now look, again, it's very similar. We've got our rotational equations over here, okay, angular, and then our linear over there. So we need to find something. We're looking for the final angular speed. So we're looking for omega f. What's in this equation? It was not in that one because that's constant. It's not speeding up or slowing down. It's not in this one. It's in that one. And it is in this one. Now we need to look for the other variables that we know. Well, we were given the initial. We were given an acceleration. We were given a time. So we can go ahead and use this very first the second equation down. Okay? So the final rotational velocity is equal to the initial plus the angular acceleration times the change in time. Write down our equation, substitute in. We do not know the final, that's what we're looking for. The initial was 2 radians per second plus the acceleration of 3.5 radians per second squared times the change in time of 2.5 seconds. Okay, well, 3.5 times 2.5 is 8 7/75. Simplify this. 2 plus 8 7/75 is 10 7/75, and it is a rotational speed, so it is in radians per second.